Welcome to this explainer. Today, we're diving straight into Chapter 10, Batch Processing, and we're going to trace the totally fascinating evolution of massive-scale data center operations. We hear buzzwords like MapReduce and data lakes literally all the time, but to really understand how we process petabytes of data today, we actually need to rewind and look at a brilliantly simple concept developed over 40 years ago. Okay, picture this. You're sitting right in front of a classic Unix terminal. You've got a massive web server log, and you need to figure out which URLs are getting the most hits. Now, instead of writing some complex custom program from scratch, you just string together a few incredibly simple Unix commands. You use awk to grab the URL from each line, you use sort to group the identical ones together, and then unique-c to count them up. You just connect them with the pipe symbol. It's elegant, it scales beautifully, and honestly, it just works. And this brilliantly illustrates a much larger philosophy. This whole vibe actually goes all the way back to 1964. Doug McElroy, the inventor of Unix pipes, said, "We should have some ways of connecting programs like a garden hose. Screw in another segment when it becomes necessary to massage data in another way. And that's it. Building small, composable tools that do one thing really well and linking them together, that is the exact blueprint we still use today to process mind-boggling amounts of data." Section 1. The Unix Philosophy Blueprint. Small tools, massive scale. So how exactly does a single machine philosophy from the 1970s map to the modern distributed data center? Well, the crucial point here is this specific set of design principles. You see, the Unix philosophy treats inputs as totally immutable. When you run a command on a file, you never damage or mutate that original file. You're just producing new output. It also completely separates the logic of your program from the wiring, meaning the program really doesn't care where its input comes from or where its output goes. This created a wonderfully safe experimental environment where you could just play with data. And modern batch processing directly inherited this exact same mindset. Section 2. MapReduce Scaling the Data Center. Bringing the pipeline to the cluster. Now, a Unix pipe is amazing, but it generally runs on just one machine. What happens when your dataset is so insanely big it needs thousands of commodity machines? Enter Hadoop and MapReduce. This system took the Unix philosophy and brought it to the massive data center scale. We can break MapReduce down into 3 pretty digestible steps. Step 1 is the map phase. Just like our awk command earlier, a mapper scans the data and extracts specific keys and values. Then, step 2, the shuffle. This is honestly my favorite part. Think of the shuffle phase as the ultimate network mailroom. It routes all the related records from thousands of different machines over the network, ensuring that all pairs with the exact same key end up in the exact same place. Finally, step 3 is the reduce phase. Like our unique command, it takes those grouped records and aggregates them. It's basically the Unix pipeline, just blown up to a massive scale. Section 3. Surviving the chaotic data center. Why MapReduce writes to disk. So why did MapReduce become the dominant force instead of traditional databases? To understand that, we kind of have to look at the chaotic environment it was born into. Google's early data centers were mixed-use environments. Batch jobs were running right alongside high-priority online services. If an online service suddenly needed more power, a batch job would just get terminated or preempted. It was total chaos. Because of this, MapReduce was designed to frequently write its intermediate state straight to the hard disk. If a machine crashed, a single task could just pick up the scraps from the disk and restart without bringing down the entire job. Now, contrast that with traditional massively parallel processing, or MPP, databases. They keep data in memory for speed, but they're highly rigid. If a single node crashes during a query, the entire query just aborts. MapReduce basically traded pure speed for ultimate scrappy survival. Section 4. The Sushi Principle. Schema on read in the data lake. MapReduce didn't just change how we process data, it radically changed how we store it. And this brings us to a really fun concept known as the Sushi Principle. The core idea here is simply that raw data is better. In traditional databases, you have to carefully design a schema up front before you can load any data at all. It's a huge bottleneck. But with MapReduce and distributed file systems, we saw the rise of the data lake. Companies realized they could indiscriminately dump massive amounts of unstructured, raw data into a cluster first and figure out what it all means later. This is what we call schema on read. It's great because it allows completely different teams to interpret the exact same raw data in totally different ways, depending on their unique needs. Section 5. The modern data flow era, moving beyond MapReduce. All right, so MapReduce was undeniably revolutionary, but it had one major flaw. It was sluggish. Let's trace this evolution real quick. Back in the 1970s, Unix pipes streamed data using small, fast in-memory buffers. Then, in 2004, MapReduce came along. And as we just discussed, to survive that data center chaos, it constantly materialized intermediate state to the hard disk. But all that disk writing made it incredibly slow for complex workflows that required chaining dozens of jobs together. So, to fix this sluggishness, the 2010s introduced modern data flow engines like Spark, Flink, and Tez. And what's really amazing is that they fixed the problem by returning closer to the original Unix vision. How do they actually do it? Well, these data flow engines treat an entire workflow of multiple steps as one giant directed acyclic graph, or a DAG. Instead of constantly writing to disk between every single map and reduce step, they keep the intermediate state right in memory. They pipeline data directly through operators, avoiding unnecessary disk writes entirely. And unlike MapReduce, which just sorts everything by default, these newer engines only sort the data when it's explicitly required. It was a massive leap in efficiency while still managing to handle failures gracefully. Section 6. Beyond the batch, the foundation for streams. Bringing it all together, what is batch processing, really? The fundamental boundary of batch processing is that it deals with bounded data. The input has a known finite size. It's historical data. A batch process knows exactly when it has finished reading the entire input, so the job eventually completes. By treating this historical input as immutable, batch processing gives us a wonderfully safe, powerful way to derive entirely new insights, like search indexes or recommendation models, without ever risking the corruption of the original source. But this naturally begs a contrast with the other side of the coin, unbounded data, or stream processing, which is continuous and operates in near real time. Which leaves us with one final, pretty provocative question: what happens when the data never stops arriving? While batch jobs might run safely overnight on a fixed set of logs, the architectural principles we just explored, immutable inputs, composable operators, fault tolerance, they lay the perfect, rock-solid groundwork for the continuous, never-ending world of stream processing. But hey, that is a fascinating topic for another explainer. Thank you so much for exploring the blueprint of batch processing with me. Keep learning, keep experimenting, and I'll see you next time.